All right, so continuing our exploration of climate change, this week we're going to look at climate data. What kind of data do we have about climate change and its effects on our world? So what we're going to be doing in this lecture is first to be able to explain how climate change can be measured. How can we put actual numbers to these processes that we've been talking about? And to understand the sources of this data. Where do we get these numbers from that show us things about how climate change is progressing in our world? So the first thing is figuring out what is it that we're going to measure if we want a measurement of climate change, right? Because this may all make sense in theory, right? The underlying scientific principles that govern how climate change works are pretty straightforward. It's a little more complicated to match that up with events in the real world. Right? Our climate system is hugely complex. So we want to match up real world data about what's really happening with our climate to our understanding of the underlying physical processes that we believe are driving it. That will allow us to make sure that our theories are correct, that they're adequately explaining what's really going on in the world. So when we look to measure climate change, we can basically measure three different steps of our model of how climate change works. So we can look at the radiative forcings. So the events that are causing climate change. So these are things like the accumulation of greenhouse gases in the atmosphere or land use change, these things that are going to cause climate change. We can measure those things. Then we can directly try to measure the energy balance of the Earth, right? The balance between energy coming in from the sun, energy going out, the temperature of the Earth that keeps those things coordinated with each other. So we can measure that energy balance. And then we can measure the impacts of climate change. So as our climate changes, that's going to create various sorts of effects on the world that are going to impact people's lives and ecosystems and all of these other things. So we could try to measure the impacts, the outcomes of climate change. So those are things like sea level rise, changes in precipitation, changes in storm intensity, all of these kind of things that we expect to be caused by climate change. We could measure those as well. So let's start with our radiative forcings. So I'm not going to say a ton about measuring greenhouse gas concentrations because we've talked about that in some of our previous lessons. If you remember the Keeling curve and the ice cores, where we're able to get those little bubbles of ancient air that are preserved, and then we can test the chemical composition of them, see how much CO2 or whatever else is in that air. Right? So we have these air sampling methods for looking at the greenhouse gas concentrations in the atmosphere that we've already talked about. We can also measure land cover change. Right? And you'll remember that that's important for two reasons. One is that it can lead to changes in greenhouse gas concentrations. Right? If cutting down forest, for example, changes how much photosynthesis is taking CO2 out of the atmosphere. If we burn stuff and so that fire puts CO2 into the air, land use change activities can alter that balance in the carbon cycle. And then land use change can also change the albedo of the Earth. And land use change can lead to more or less of that insolation getting reflected off the Earth, not absorbed and re-radiated as that long wave energy. And so for looking at land cover change, our best data from that comes from satellites. We have a whole network of satellites orbiting our Earth using various sensors to sense what's going on the surface of the Earth. Probably the most important satellite for looking at land cover change is called Landsat. So there's been a series of satellites in the Landsat program. First one launched back in 1972. So it's one of the longest records that we have of satellite observations of the Earth. It has a 30-meter resolution, which basically means if you were to zoom in on Landsat data, each little pixel, each little square of data that we get covers an area 30 meters to a side, 30 meters square. So that's a pretty decent resolution when you're looking at this kind of regional or global scale changes, right? You don't need finer resolution than that. It would just inflate the size of your data sets to have so many more pixels going on. There are satellites with much finer resolutions down to a few meters for other sorts of applications where you do need that greater detail. And so what you see in the map there is an illustration of how we can look at land cover. So one of the big kinds of land cover change that humans are responsible for and that contributes to changes in climate is deforestation. We take forested areas, cut them down, they'll end up being replaced usually by cropland or grazing land, or sometimes by like urban development and so forth. And so that map is showing you green are the areas that are continuously forested during the period of that study from 2000 to 2012. Red areas became deforested during that time period. You'll also see a few little purple blips on there that indicate reforestation, areas that were not forested in 2000 that grew forests during that period. It's a much smaller percentage of the land than the deforestation. And I actually chose that map because I think it's actually a bad map in one important respect. So this is going to be a little bit of a tangent, but I think it's an important one to keep in mind when you're looking at maps as sources of data. So when we make a map like this, we're trying to take the round world and we're trying to put it on a flat screen here. All right, we're going to take the surface of the Earth and smush it and stretch it out flat so that we can see the whole world at one glance on this map. And to do that, you're going to distort certain things. And to greatly simplify what we could spend an entire semester studying, there's two things that you could distort. You could distort the shapes of things, or you could distort the sizes of things. And in this case, the people making this map have decided to go with distorting sizes rather than shapes. They're using something called the Mercator projection, and they've done something a little bit sneaky, which they've left Greenland off this map. If you see, there's a big gap between North America and Iceland on this map. That's where Greenland should be. But looking at Greenland is one of the kind of easy ways to tell that you're looking at a Mercator projection, because Mercator projection tends to inflate the sizes of things closer to the poles. And so it makes Greenland look the same size as Africa, when in fact Greenland is much, much smaller than Africa in the real world. And they've kind of sneakily left Greenland off this map to make it a little less obvious that they're using the Mercator projection, which increases the sizes of things near the poles. The trade-off is that it keeps the shapes of land masses more accurate. But in this case, if we're trying to understand the amount of deforestation that's happened on the Earth, you would really want a projection that keeps the sizes of things accurate, right? That keeps the areas correct relative to each other. So I think the Mercator projection was a bad choice for this particular map. It's making those northern forests in places like Canada and Russia, making the area of those forests and the deforestation that's occurring there look much bigger relative to the tropical forests in Africa, Indonesia, Brazil. Those relative sizes are skewed from each other. So always be careful when you're looking at a map like this to think about what projection are they using. Is it preserving the things that you want preserved? So if this is something like area being deforested, you really want an equal area projection, one that keeps the sizes of things the same. Okay, so that is measuring our radiative forcings. We can also measure the energy balance. And the main piece of information that we can get there is the Earth's temperature. Right? And you remember the Stefan Boltzmann equation, that the temperature is what keeps the energy in, energy out imbalance. Right? If we're getting more energy in, the temperature will rise, and that will lead to more energy going out until those things get in balance, or vice versa. If we get less energy in, the temperature will drop so that radiation out, energy out drops. So to measure our temperature of the world, one way we can do that is simply with a thermometer. Anybody can take a thermometer, go outside, see what the temperature is. But if we want to talk about global temperature, if we want to understand the temperature of the whole Earth, we're going to need a lot more thermometers. We're going to need a network of thermometers making measurements all around the Earth. And so It's not until about the 1880s that we get enough people spread widely enough across the Earth making reliable, regular measurements of temperature, right? Recording it every day with good quality instruments and reporting it so that we can bring all this data together to sort of accurately estimate the global temperature. That really starts in about the 1880s up through the present. So that's as far back as we can go with these direct measurements of temperature. What you see on the map there is all of the sites of the Cooperative Observer Program, which is the program that generates this kind of data for the United States. Or you see the lower 48 states there, of course. So each of those little blue dots is a weather station that is taking these temperature measurements throughout the day, reporting them all into a central database so that we can calculate our average temperature. So there are over 11,000 of those weather stations in the United States. And as you look at that map, you'll see those weather stations are not evenly distributed across the country. There are some areas that have a very dense set of weather stations. So Pennsylvania, you can see, is pretty densely covered with weather stations as compared to, say, Nevada, where they're much more sparse. And, that kind of makes sense, right? Most of Nevada is desert. There's not a lot of people there to maintain those weather stations. But that does mean that if we want to go from the observations of each of these weather stations for their particular local area, and then use that to calculate an average temperature, we need to do some adjustments. We need to take into account the fact that some areas we're going to get lots of closely spaced observations, other areas they're more spread apart. And so there are slightly different ways that you can do that you can try to account for things like unevenness of coverage of these weather stations. And so when we look at our global temperature data, you have a slightly different data set published by 4 major organizations that do this work of collating all of these temperature readings and turning them into these broader average numbers. So 2 of them are generated by the US government. You have NOAA, the National Oceanic and Atmospheric Administration. They do a data set. Then NASA does their own data set. Then you also have the Hadley Center at the University of East Anglia in the United Kingdom. And then there's the Japanese Meteorological Agency. So you'll sometimes see slightly different global temperature data because it may be coming from a different one of these 4 organizations, but broadly speaking, they're all in agreement. They're not wildly different from each other. They're just very slightly different from each other because they all have to make assumptions and use modeling to even out these gaps that we have in our data. We can also measure temperature from satellites. So we have satellites orbiting the Earth. They can measure the energy coming off the Earth and use that to figure out our temperature. Satellite data only goes back to the 1970s. So we have a 100-year gap where we have surface temperature, thermometer-based readings, but we didn't have any satellites up there to double check it. Satellites are also nice because they can give us even coverage across the whole world, land and water together. And satellites can also measure the temperature at different layers of the atmosphere. So our weather stations that you saw there are basically recording temperature at ground level. But satellites can measure throughout the atmosphere. So we can look at how that energy is progressing up from the surface up through the atmosphere, where it's being absorbed by greenhouse gases and radiated back down, and where it's managing to escape from the Earth. And then we can also project our data farther back by using what we call proxies. So, we only have really solid direct measurements of temperature going back to the 1880s or so, but we do have other records that can tell us something about the global temperature. So these include things like less systematic historical records. So for example, we have diaries from medieval monks where they would note what day the pond at the monastery first froze in the winter and what day it finally thawed in the spring. That gives us an idea of what the climate was like, what the temperatures were that they were experiencing, going back all the way to whenever those monks started keeping their diaries in the Middle Ages. So that goes way back farther than the temperature records we have. The catch is that's only data about that specific monastery and its immediate surroundings. So we have to see if what's going on at that one place, how well that correlates with global trends to try to use that data to take our records further back than we have the sort of comprehensive direct measurements. We can use tree rings because the size of the rings that trees grow varies depending on the climate that they're experiencing each year. So we can use tree ring data to get some information about past climate conditions. The growth of coral does the same thing. Coral grows differently depending on the temperature that it's experiencing that year, and so we can look at a cross-section through a coral reef and find out something about past temperatures. We also have those ice cores. So in addition to trapping little bubbles of gas, we can look at things like the thickness of each layer of ice that accumulated each year. And that'll tell us something about past temperatures. So all of these proxy records, they're not direct measurements of temperature, but they're things that tend to correlate with temperature. And so we can use these to figure out temperatures going back farther than we have these direct records of, albeit with some significant error bars to it. So what you're seeing on the graph there, the black line is a smoothed trend of these reconstructions of temperature based on a whole variety of proxy records. The blue is the year-to-year unsmoothed data from the proxies. The red is the direct instrumental measurements. So you can see that comes in at the end, and there's sort of an overlap period that we use to calibrate our proxies and figure out what conclusions to draw from them. And then the gray around it is the error bars. So our estimates of past temperature based on these proxies are not exact. They've got some wiggle room to them. But what you're seeing on this graph is that based on these proxies, the temperatures that we're experiencing in recent times, and you'll see this graph only goes up to 1998. It has gone way up past that in the subsequent 30-some years. You'll see our current temperatures are way above anything that was experienced going back 1,000 years. And I'm using this particular graph, this one that only goes up to 1998, because this is one of the most famous graphs in climate science. It's called the hockey stick graph because the shape of it's kind of like a hockey stick. And you've got that long, slightly downward sloping shaft to the stick, and then the blade that shoots up in the last century or so. And that this graph was very famous because it so clearly illustrates how different our temperatures have been over the last century or so, how far outside of the historical norm that we've gotten since the start of industrialization, since these major changes that human activity is causing to our radiative forcings. So on that graph, you may have noticed that that wasn't showing temperatures, it was showing temperature anomalies. So you may have wondered, what is a temperature anomaly? Well, of course, an anomaly means something that's unusual. So a temperature anomaly tells you how much warmer or colder a given temperature reading is compared to some sort of historical average. So you've got the average, then any 1 year's temperature is going to be probably a little above or a little below at least that average temperature. And so how far you are off from that average is your anomaly. And so as a kind of illustration, we can calculate anomalies for anything where we have an average and then individual data points. Right? It's not just about temperature. So to kind of illustrate the concept, here's an example of two hypothetical students that each took a class that had 4 exams in it, and they got graded on each of those exams. So Alex got grades of 88, 72, 84, 92. That's an average of 84 across those 4 exams. See, Skylar didn't do so well, got grades of 62, 53, 66, 67 for an average of 62. So then we can calculate the anomaly for each of those exams by just looking at the difference between the student's score on that exam and their average. So Alex on exam 1 got an 88 as compared to an average of 84. So Alex's grade anomaly for the first exam was a 4. Then getting a 72 on exam 2 was a grade anomaly of minus 12, 12 points below their long-term average, etc. for all of the other scores that we see here. And the reason that I put this up here is to illustrate that anomalies are relative to your long-term average, which means a higher anomaly doesn't necessarily mean a higher amount of whatever it is you're measuring. Right? So if we look at exam 2, for example, Alex has an anomaly of -12. Skylar has an anomaly of -9. So Alex has a bigger negative anomaly on exam 2, right? Alex underperformed their long-term average by more than Skylar underperformed their long-term average. And yet Alex still did better on that test. Alex got a 72, Skylar only got a 53. So Alex did better on the test, but was farther off from their long-term average, did worse than their long-term average by a larger amount than Skylar did, because Skylar's grades are all pretty bad. So 53 is not as unusually bad for Skylar as 72 was for Alex. And that's important to note because when we look at temperature anomalies, if we look at them, not the full global temperature anomaly, but we look at it place by place, right? What's the temperature anomaly for particular locations on the Earth? We tend to find that polar areas, areas near the North and South Poles, tend to have larger temperature anomalies. They've gotten warmer relative to their long-term average, whereas more tropical areas have not warmed to the same degree relative to their long-term average. But that doesn't mean that the poles are warmer than the tropics. The poles are still colder. They've just warmed up more than the tropics have. So you can see this on this map. This is temperature anomalies across the Earth for October 2022 relative to the average from 1991 through 2020. So you can see for most of the world, we've got positive temperature anomalies. Most of the world in October 2022 was warmer than the 1991 to 2020 average, sometimes by a pretty substantial amount. You see in places like Greenland, central Siberia, Europe was quite a bit warmer than average in October 2022, though there are also some parts of the world that were a little bit colder than average. So the eastern United States was a little bit colder than average during October 2022. Australia was colder than average in October 2022. So for this 1 month, we've got some positive, some negative anomalies depending on where you are, though overall we've got a lot more positive than negative anomalies going on across the world. And you see that phenomenon that I mentioned where the polar areas tend to have higher temperature anomalies than some of the tropical areas, even though tropical areas are overall still warmer. Polar areas have just gotten warmer relative to their own long-term average. So now let's look at how we can measure the consequences of climate change. So in order to do that, we're going to talk about what some of these consequences are, right? What are some of the things besides simply increased temperatures that we expect to see as a result of climate change, and how can we measure those things? So one pretty straightforward consequence is a reduction in snow and ice cover on the Earth's surface, right? If the Earth is warmer, there's going to be less snow and ice sticking around on the surface. And we can measure that by ground-based observations. The people at those weather stations that we saw on the earlier slide, in addition to measuring temperature, they're going to look at things like snowfall and how long that stays on the ground. And then you've also got satellite data. Satellites can very easily observe how much ice or snow is on the ground each time that they pass over. And on the graph there, you see one very important place that we keep track of snow and ice cover, which is the Arctic Ocean. So the Arctic Ocean typically would largely freeze over during the winter, and then it would melt back somewhat during the summer, and then expand again, cover most of the ocean during the winter with ice. So what you can see on that graph there is that the extent of the ice in September, so that's when that ice is at its smallest extent, right? That's the very end of the summer. So that ice has shrunk down as small as it's going to go for that year before it starts to grow again in the winter. So we're taking that minimum ice extent for the year. You can see a pretty clear downward trend in how many million square miles of ice we have in the Arctic Ocean, starting back in the 1970s when we started getting good satellite records of this down through the present day. And you can see the little maps there give you, an illustration of what that looks like, right? So 1979, 2.7 million square miles of ice. You can see that filling up most of the Arctic Ocean, even in September at its smallest extent during the warmest bit of the year. By 2021, you can see that the ice cover is much smaller. There's a lot more open ocean visible there around that ice cap. So why do we care about this? Well, it can have significant ecological effects. There's lots of species that depend on cold and ice for part of their life cycle, and so those species would be negatively impacted. So polar bears are kind of a famous symbol of climate change because they depend on ice to walk around on, to go hunting and so forth, and so they can be pretty negatively impacted if there's a lot less ice up there. On the other hand, there are some species that are held back by cold conditions and ice and snow, and those species have expanded as a result of decreasing ice and snow. And unfortunately, some of those species that have benefited are ones that are not so good for us. So ticks, for example. We've seen an expanding number of ticks in our forests because our winters have gotten milder, so they're not being killed off during the winter in the same way that they used to. The loss of specifically this Arctic ice is also creating new opportunities for shipping routes and mineral exploitation. So if you look at that lower map there, the 2021, you'll see that there is an open ocean route around the the upper on the map. It's all south going out from the center there, around the top end on the map of that Arctic ice that's basically between the ice and the coastline of Russia there at the top of the map. And so ships are now being able to cross through the Arctic Ocean there, and that drastically cuts your shipping time if you're traveling between, say, Europe and Japan or China or Korea. Much quicker than going down around the bottom of Africa or even through the Suez Canal to make that trip. You see, we're also getting close to having open water that you could sail through around the top of Canada as well. That would also potentially really cut the travel time from the eastern United States to East Asia and back. You can also access a lot of minerals that were sort of hidden under that ice where it was impractical to mine them or drill them before, but now with less ice you can get at them, and that's creating actually a lot of conflict between the countries that claim territory in the Arctic. Things that were not valuable territory to hold on to because they were too frozen are now becoming very valuable because there's potential mineral resources there, and it's leading to potential conflicts among Arctic nations. This loss of ice cover in the Arctic is also a good illustration of how we can get a positive feedback. So a positive feedback is a feedback where some process amplifies itself over time. So positive does not necessarily mean good. In fact, a lot of positive feedbacks are bad things. But positive means that it's moving in a plus direction, that it is adding to itself over time. So we have a change in a system that causes some other change, which in turn amplifies the original change. So a very straightforward kind of feedback in our climate system is called the ice albedo feedback. So we get increased temperatures. That leads to the melting of sea ice, as we saw on the previous slide. When that sea ice melts, that decreases the albedo of those areas. If we go from bright white sea ice to dark colored water, that's a huge drop in albedo, right? Way more of the sun's energy is now going to get absorbed by that water, energy that would have been just reflected away from the Earth by that bright white ice. So this decreased albedo, and we should know that decreased albedo, more of that insolation being absorbed, that's going to lead to increased temperatures. Those increased temperatures are going to in turn melt more sea ice. So we're going to get this loop where the temperatures keep increasing and increasing. And the only thing that would stop this is either some other factor that puts the brakes on that increased temperature, some other influence on temperature that overwhelms the impact of the decreased albedo from the sea ice melting, or if we just run out of sea ice. Once there's no more sea ice, you can't continue to increase the albedo by melting away that sea ice. So this is an illustration of a positive or amplifying feedback where we get increased temperature, leads to sea ice melting, leads to decreased albedo, leads to increased temperature again. Another pretty well-known impact of climate change is sea level rise. So with sea level rise, we're not talking about the melting of sea ice. So all of that ice in the Arctic Ocean that we were just looking at for the last couple slides, that's irrelevant to sea level rise as far as adding water to the ocean, because that ice is already in the ocean. So if you have a glass of water with some ice cubes in it and those ice cubes melt, it doesn't make your glass overflow. That water is already in the glass, it's just changing from a solid state to a liquid state. What does add water to the ocean is the melting of ice that's sitting on continents. So when you have large masses of ice that are sitting on a continent up out of the ocean and those melt, that does add new water to the oceans. So our major continental ice sheets that make a significant contribution to sea level rise are the ones in Greenland and in Antarctica. So melting of continental ice sheets is contributing to sea level rise. The other piece of sea level rise that also makes a pretty significant contribution is thermal expansion. So the water that's already in the ocean will expand just a little bit as it gets warmer. So as you heat up water, it swells up just a little bit as it gets warmer. So all of that water that's already in the ocean is going to expand a bit, and that's going to raise our overall sea level. So what you see on the graph there, this is sea level rise. The black shows our measurements of sea level rise based on satellites. So our satellites can tell how high the sea level is. They can measure that directly. And then the red and blue lines show us the components of that we can attribute to thermal expansion and added water. So that's mostly meltwater from those glaciers. You can see that added water is contributing, about half again is more than thermal expansion, but the thermal expansion is making up a pretty significant portion of our sea level rise. So you want to remember that it's a combination of melting glaciers and expansion of the water already in the ocean that contribute to our sea level rise. And you can see that the overall sea level rise since the beginning of this chart in 1993 has been not quite 10 centimeters. And in fact, this chart is a little out of date. It's a few years old at this point. So we're probably at about 10 centimeters of sea level rise over that period if we take it up to the present. So we've got this rising overall global sea level. It's important to keep in mind that other factors can affect the local conditions. So where exactly sea level comes to on a specific beach or coastline is going to be affected by global sea level rise, but also some other factors. There can be erosion or deposition going on at that location. So for example, we're losing a huge amount of land in the Mississippi Delta. The ocean is really encroaching on that. Some of that is due to sea level rise. Others of that is due to the fact that a variety of things that we've done to try to tame the Mississippi River have led to a big reduction in the deposition of sediment at the mouth of that river. So we're not replenishing the dirt that makes up the delta because it's getting stuck behind dams and stuff farther up the river, and so that is accelerating the encroachment of the sea onto the Mississippi Delta. Right, so we have this other factor of erosion and reduced deposition that's affecting sea level at that particular location. We have post-glacial rebound. So in areas of the world that used to have a gigantic ice sheet sitting on top of them during the last ice age, the ice squished down the rock. And we're still kind of rebounding. The rock is slowly bouncing back from not being weighed down by all of that ice. So that leads to actually what looks like decreasing sea levels in some parts of the kind of northern parts of the world because that post-glacial rebound is larger than the sea level rise that is happening. Coral growth, whether the corals are growing more or less depending on local conditions, can affect where the coastline of a coral island is located. So all of these things can layer on top of sea level rise. They can change conditions at localized area. But if we want to look at this global sea level rise phenomenon, our best way to do that is with these measurements from satellites. The satellites can measure the average height of the sea around the world and allow us to factor out all of those very localized issues to look at our global sea level rise, which, as you can see from the chart there, is pretty significant, pretty steady upward trend in that sea level rise. And here on this chart, you see some projections into the future based on climate modeling. We're going to talk a lot more about climate modeling in our next lecture. But I'm putting this up here now to show you, this projected sea level rise under different sorts of climate change scenarios, because sea level rise is something that responds fairly slowly to temperature increase. So the amount of melting of the continental ice sheets that we've seen thus far is not all that we're going to get for the current temperature that we were at. If we were to stop our temperature from rising, if we just lock it in at the current temperature, ice would continue to melt and sea level would continue to rise for quite some time until the system came into balance again. So it's a longer term process. Same thing with the thermal expansion in the ocean. That's going to take a while to fully play out, even with the temperatures we're at right now. So this is something that is likely to continue even after we stabilize global temperatures, assuming that we do manage to stabilize our global temperatures, because it's just a slower process. But even the small increases that we're seeing already can be a big threat to low-lying places. So places like Bangladesh or Florida that are very close to sea level already. A little bit more sea level rise could have pretty devastating effects on people that live in the coastal areas of those. At particular risk are the small island nations. So we have countries that are located on small coral islands in principally the Indian and Pacific Ocean. So these are countries like Kiribati or the Maldives, that the highest points in these countries are sometimes only a few meters above sea level. So if we get a meter or two of sea level rise, that could put these countries entirely under the water. So some of these countries have been some of the most outspoken advocates for the rest of the world to do something to deal with climate change, because they stand to lose their entire country if sea level rise continues on its current trend. Kiribati right now is actually in the process of purchasing land in Fiji, where the islands are taller. They're volcanic islands that stick farther out of the water, for their people to move to if and when they lose their current islands, if they go entirely under the water. And as a sort of side note there, the spelling there may look like it's Kiribati, but it's actually pronounced Kiribati. So in the spelling system that's used in Kiribati, they use a TI to represent the S sound for reasons that are, be too much of a tangent to get into in a science course. But so when you see the name of that country that's very prominent in discussions about sea level rise, it's pronounced Kiribati, not Kiribati. Another consequence that we may see from climate change is increased hurricane activity. So we'll start by talking a little bit about what hurricanes are. So a hurricane is a tropical storm with winds of at least 119 kilometers per hour. So hurricanes are basically giant tropical storms. The destructiveness of hurricanes is largely a product of those very fast winds. And hurricanes are driven by warm water. So when water evaporates, it picks up energy. That's why sweat cools you down, or spraying yourself with some water cools you down, because as that water evaporates off your skin, it sucks up energy. And so by sucking up that energy, it cools you off a little bit. So water is taking in energy as it evaporates. But then when that water condenses, when it comes back into liquid form, it's going to release that energy. The energy that got sucked up in the process of evaporation comes back when it condenses. And so a hurricane is made up of clouds. So clouds are the result of evaporation of water from the sea and then condensation as it cools off higher up in the atmosphere, right? Bringing back that cycle of evaporation and condensation that we talked about many lessons ago. It all comes back around, right? So if you have warmer water, you're going to get more evaporation, which means more energy being sucked up by that evaporating water, and therefore more energy released when that water condenses and forms the clouds that make up the hurricane. So we expect that warmer conditions around the world are going to put more energy into our hurricanes. So in order to see if this is really occurring, we have to be able to measure the strength of our hurricanes. And there's basically two ways that we talk about the strength of hurricanes. So one is the category system, or the Saffir-Simpson hurricane wind scale. And so this divides up hurricanes into 5 categories. Category 1 being the weakest, Category 5 the strongest, and it's based on the top wind speed in the hurricane. Okay, so you become officially a hurricane at 119 kilometers per hour. At 153, you transition from being a Category 1 hurricane to a Category 2. After 177 kilometers per hour, you become a Category 3, etc. You don't need to remember these numbers that designate the different categories. Key thing is just to remember that the higher the number of category, the stronger the hurricane is, and the Category 5 is our top hurricane category. Those are the strongest hurricanes that we've got. And we're measuring it by wind speed because that's what does most of the damage. When a hurricane hits, it's really the wind speed that is causing the most destruction. It's the thing that really we want to worry about if we're in the path of a hurricane. Another way that we might measure the strength of hurricanes is something called the power dissipation index. So this is a measure of the total amount of energy being released by this hurricane. Right? Hurricanes are these collections of energy, right? This energy that's being sucked up by evaporating water and then released as it condenses into these clouds. This is putting all this energy into the hurricane and powering it. And if we measure that total energy that a hurricane is releasing, that's another way of looking at the strength of hurricanes. So here we've got some hurricane data. So this is specifically Atlantic hurricane data. So the hurricanes that hit the Atlantic coast of the United States, Caribbean, Central America, and so forth. So if you look at the first graph there, that's just the number of hurricanes. And what you'll see is there's not much of a trend in number of hurricanes going back to the 1880s. Right? It is pretty flat, whether we're looking at just the red line, which is the hurricanes that make landfall in the United States, or if you look at the lines above it that are the total number of Atlantic hurricanes. And one thing to note there, you'll see that for that total line, there's unadjusted and adjusted. And that unadjusted line looks like it's got a bit of an upward slope, but then that gets canceled out if you switch to the adjusted line. You'll notice that we start making those adjustments in about 1970. And that's because of availability of data. So starting in the 70s, we have those satellites that I've been talking about repeatedly. A satellite can keep an eye on the entire world. Okay, so if a hurricane is going on anywhere in the world, a satellite can spot that. Right? Satellites are just observing everything as they fly over. Before the 70s, we didn't have satellite data, so we had to rely on ground-based observation. To know that a hurricane was happening, it had to either make landfall somewhere where people lived, so that those people would see it, or it had to cross the path of a ship on the ocean, so that the sailors on the ship would see it. It also had to not, destroy the ship so that the sailors could make it back and report. So that means there were some hurricanes that might go unnoticed. That the hurricane rose, it existed, and it dissipated before it got to a place where there was any person to observe it and make note of it. So that adjustment is basically trying to say, okay, well, we've observed X number of hurricanes, and we know there was this much area not being monitored at all. There was nobody there to have noticed a hurricane if there was one. So we can take a sort of an educated guess at how many hurricanes might have gone unnoticed that year in order to in order to sort out the, what was likely the total number of hurricanes and to adjust for this incomplete observation that we may have. So that's why we have that adjusted line. And you'll see that adjusted line gets rid of any apparent trend in number of hurricanes. So it doesn't seem like climate change is causing there to be more total hurricanes. But on the second graph there, that's showing the power dissipation index for hurricanes each year. And you'll see that the power dissipation index does have an upward trend, particularly since about the 80s, which is when we really also see the big increases in surface temperature kicking in. So what we've got there is evidence that hurricanes, we're still getting the same number of hurricanes, but they're getting stronger. We're getting bigger hurricanes, hurricanes with more intense winds, hurricanes that are falling more into the higher categories of the Saffir-Simpson scale. So here again, we can see a way to measure a particular consequence of climate change looking at the power of the hurricanes. So then the last thing that I want to say a little bit about is the concept of attribution. So attribution is the process of determining the degree to which a particular cause is responsible for a particular effect. So in the context of climate change, attribution is trying to determine how much is climate change responsible for a particular event. So we can look at a single weather event, a particular hurricane, a particular drought, a particular blizzard, whatever sort of weather event, individual single weather event we want to look at. To what degree was that event caused by, or at least made more severe by, climate change? There's been a huge growth in attribution studies over the last couple decades. So it's now routine after any sort of outstanding weather event, any really noticeably big hurricane or drought or other sort of storm or whatever might happen, somebody's going to do an attribution study to try to see if climate change can be blamed for this event. And you see there in the graph, that's just a summary of attribution studies done between 2004 and 2018 and what their results were. So you see a whole lot of attribution studies done on heat wave. Vast majority of them concluded that climate change made that heat wave more severe or more likely to occur than it would have been without climate change. See quite a few on droughts and rain and flooding events. Again, most of those, the studies concluded that climate change made that event more severe, more likely to occur. Oceanic events, mostly attributed to climate change. You see cold, ice, and snow events. The majority of those attribution studies have concluded that climate change made those less likely to occur, which should make sense, right? Climate change is making it warmer, so that should make cold snaps and stuff less likely to occur, and then just general storms there at the bottom. So this is just summarizing, what studies have been done. But you see most of these attribution studies have concluded that climate change is making the events that they looked at more severe, more likely to occur. But there are still a substantial number of them where they didn't document an effect from climate change or where the data was inconclusive. It couldn't clearly come to a conclusion based on the data they have. So what I would recommend is that if you're talking about a single event, right, you're looking at one particular hurricane and people are talking about, was this caused by climate change or not? It's usually better to say climate change is making events like this more common rather than to say this specific event was caused by climate change. Okay, so that particular hurricane that you're talking about, rather than trying to pin that one hurricane on climate change, it's usually better to say this is the kind of thing that we're going to tend to see more of as a result of climate change. And that's not quite as snappy of a conclusion to make. It's not necessarily going to be a knockdown political argument or anything, but I think it's a little more accurate to what we can say scientifically speaking. So for your lab assignment this week, we are going to be looking at how we can visualize climate data using Excel. So you're going to get some practice with a very common program that you may end up using in a variety of other applications throughout your college career and your job career after that. We're going to use climate change as our reason to see some of the things that you can do with Excel in order to visualize some of this climate data and then do some very basic mathematical operations to test relationships between climate change and its possible causes. So that's your lab assignment, and I will talk to you next week.